Learn how to draw our electron dot structures, and then this module we're getting into what shapes we get out of that. And so what we have here is we've got our electron dot structure for carbon dioxide and our electron dot structure for water. And these are models of carbon dioxide and water. Are they the same shape?
No.
Do they both have the same number of atoms?
Yeah, they both have 3.
They both have 3. So what's different between carbon dioxide and water?
Well, this one's got 2 loopy things, and this has got little paddles.
Right. It's got little ear-looking things. If we look at our electron dot structure, what do we notice about our carbon dioxide?
It matches.
It matches. It's got our 2 bonds. Does it have anything else on carbon?
No.
It's just got the bonds. Here, we've got our bonds. What do we have up here?
We got lone ones.
We've got lone ones. And so what do we think our little ears represent?
The paddles are the lone.
These are our lone pairs. And so what did we learn when we looked at our PhET simulation? Well, and actually even before that, what do we know about electrons? What kind of charge they have?
They're negative.
They're negative. And if we've got negative things and negative things, what are they going to do to each other?
They push.
They push. They're like magnets. When you try to put 2 north poles together, they're going to push apart. So electrons want to be as far apart as possible. Here, we just have the bonds. They're going to push all the way apart and be linear.
Like a line.
Like a line. Here, we've got our bonds that are pushing apart, but we also have our lone pairs that are pushing apart. And so what does that do for our shape?
Bends it.
It bends it. So our shape is
Bent.
bent. This is what water looks like if we don't include the lone pairs. But it's bent because of the lone pairs.
Bent.
Yeah, whenever you're ready.
All right. So we just looked at comparing carbon dioxide to water. And so carbon dioxide had no lone pairs, it was all in a straight line.
Linear.
Water had 2 lone pairs, so it was
Bent.
because our electrons push away. So the next one we want to compare is NH3 and BF3. So what does NH3 have if we look at this and we look at our structure?
They've got the lone pair.
They've got the lone pairs. And so what does that do to all of our atoms that are bonded?
It pushes them.
It pushes them down. And so what kind of shape does this make?
It's like a pyramid.
It's like a pyramid. It's a trigonal pyramidal. What does it mean that it's trigonal?
Tri
3. All right. So this is also trigonal.
Yes.
But what's happened to this one?
It's flat.
It's flat. And so in math, we learned that things that are all in the same flatness,
Are on a plane.
they're on a plane. So it's trigonal planar. And so B doesn't have any lone pairs. It's just
Flat.
flat,
Like a plane.
like a plane. All right.
Not this kind of plane.
We've looked at some different shapes. Now is our last shape. So this one is CH4. And so we have just bonds around. Do we have any lone pairs?
No.
So what are all our bonds doing?
Pushing.
Pushing. And so they all push out to different corners. What's this one called?
Well, when you had it like that, it looked kind of like a pyramid.
It was kind of like a pyramid,
Kind of.
but not really. This is actually one of our weirder names. It's a little harder to remember. It's tetrahedral.
Because tetra is 4.
Because tetra is 4. Think like Tetris. All your pieces have 4 parts. So it pushes all of our bonds apart
Equally far.
equally far. And so it's tetrahedral. How many atoms are in this?
5.
5, but how many atoms are around?
4.
Anytime we got 4 atoms around, it's going to have to be tetrahedral. That's the only thing we can do. So, to remember, if we've got 4 atoms around, it's
Tetra.
tetra, it's tetrahedral. If we only have 4 atoms total, and so we have 3 atoms around, it could be 2 things. They're both going to be
Tri.
they're both trigonal. This one is
Pyramidal.
pyramidal. It looks like a pyramid. What does it have that this one doesn't?
Lone pair.
Lone pair. This one is going to be trigonal
Planar.
planar because it's all flat,
Yes, like a plane.
like a plane. And so then, if we've got 3 atoms, we've got 2 choices. We have
Linear.
linear, it's all in a line, and we have
Bent.
bent. And so what makes this one bend and this one not?
Lone pairs.
Lone pairs. In general, we would have to make sure that our electrons are pushing as far apart as possible. This is why overall the study of the shapes of molecules is VSEPR. Valence,
Electron.
shell,
Oh, shell.
electron,
Electron.
pair,
Pair.
repulsion.
'Cause
All
they're
our
pushing.
they're pushing. All our electrons are pushing away. So now that you can find the shapes of molecules, you can now also determine if a molecule is going to be polar. So we talked in 4.2 about finding if bonds were polar covalent. This is largely based on their electronegativity difference. You're going to look for an electronegativity difference between 0.3 and 1.7 to get a polar bond. Don't worry about exactly 1.7. You'll find some things we classify as polar covalent that are more like 1.9. Bond polarity is more of a sliding scale. It's not a hard and fast sort of thing. So it starts to become more ionic, but we still classify it as polar covalent. If I've asked you to find if the molecule is polar, unless it's really extreme, assume that I really mean for that. Our more electronegative atom will keep more of the electron density. If you're trying to figure out what your electronegativity difference is, you're going to look for a table like this. If you just search for periodic table electronegativity, you'll find a picture that shows all of your electronegativities, and you just take your values. Be warned, some of the values get a little bit different, but again, as if we're looking for more a general range than an exact number every time, it's okay. The slightly more complicated question is if our molecule is going to be polar. If we're trying to decide if our molecule is going to be polar, think about our polar bonds like they're in a tug of war. If everybody's pulling exactly fairly, nobody moves. So even if it's a really polar bond, if it's the same all the way around, nothing's going to happen. The molecule's still going to be non-polar. If someone wins, we consider it polar. If it's non-polar, it's because everyone pulls equally. So if you have 4 big, equally strong guys, you're still not going to have anybody win at tug of war. If you've got 3 strong guys and 1 kind of wimpy guy, somebody's going to win. And so that would be polar. Shapes to look out for that are always going to be polar if your bonds are polar are bent and trigonal pyramidal, because those lone pairs make your molecule uneven and gives you a place where you're not pulling evenly because there's not an atom there. So if we look at our examples down here, NH3 is trigonal pyramidal. You've got your H's down here. You've got your lone pair up here, which is getting more of your electron density, so that makes it polar. In water, again, we've got our H's down here, we've got our lone pairs up here, and so water is polar. Things that are linear that have an electronegativity difference have to be polar as well, because if my H is pulling a lot more weakly than my F, I have a polar bond, and I have to have a polar molecule if I have a polar bond if it's linear. In something like CH4, everybody's pulling symmetrically. So yes, we've got a partial positive here, that's a partial, and a partial negative in here, but they all go around and cancel each other out. So this is overall non-polar, because everybody's pulling evenly all the way around. So let's do a couple of examples. The first thing you're going to have to do when you're doing one of these is draw your Lewis dot structure, because you need to know what shape you're going to get. So if we're drawing BF3, we know that B comes with 3 valence electrons. That's going to be our central atom because we only have 1 of it and it's our least electronegative. Then we fill in our F's. And there's 7 valence electrons. So now we've got 3 bonds and no lone pairs, because we've got 1, 2, 3 bonds on boron. There's not a lone pair down here. So if we look at our table from our first PhET simulation, we see that 3 bonds and 0 lone pairs is going to be trigonal planar. And so these are flat in the same plane with all of our fluorines equally spaced around pulling. So because this is flat and symmetrical, all of my electrons are getting pulled by my fluorines, but nobody's winning because it's all even. So even though, if we look at our periodic table of electronegativities, fluorine has electronegativity of 4, and boron has electronegativity is going to be 2.0. So that's an electronegativity difference of 2. But all of our fluorines are pulling equally, so it's going to be a nonpolar molecule. Even though our bonds are very, very polar. So let's look at NF3. We're going to start out very similarly with NF3. We know N's are least electronegative, so it goes in the middle with its 5 electrons. Then we're going to fill in our fluorines around and fill in their 7 electrons again. So our biggest difference is boron did not have a lone pair, nitrogen has a lone pair. And so if we look at our table, we find that 3 bonds in 1 lone pair is going to be trigonal pyramidal. If we look at our electronegativities, we know our electronegativity difference is going to be a little bit smaller this time because fluorine still has electronegativity of 4, but nitrogen's got an electronegativity of 3.0, giving us an electronegativity difference of 1. It's still in our range to be polar. But if we look at how our molecule arranges itself, trigonal pyramidal, remember, you've got one central atom up high, and then all your bonded atoms are kind of folded down below with your lone pair up here by itself. Because of that lone pair, all of our fluorines are pulling down and away. There's nothing to counteract it with our lone pair, so our molecule ends up polar, even though our bonds are less polar than they were in BF3. Now, our last 2 examples. We're going to compare CH4 and CH3Cl. CH4 we know, we've done this a lot. C comes with 4 valence electrons. We put our 4 hydrogens around. And each hydrogen only comes with 1 electron. So each is going to bond once. So we look at our electronegativities. C comes with an electronegativity of 2.5. H comes with electronegativity of 2.1, which gives us a difference of 0.4. So this is a slightly polar bond. But our shape, remember, if we've got 4 bonds and no lone pairs, is going to be tetrahedral. So everyone's going to pull, all of our H's are going to pull evenly around, or be pulled from evenly around. So we've got, everything's getting pulled in toward carbon, but because it's being pulled in evenly, this is a non-polar molecule. If we look at CH3Cl, we still put our C in the middle with its 4 electrons. We put our H's on 3 sides. We fill in all the electrons. Now we've got to look at a couple different electronegativity differences. We've got to look at the difference for anything bonded together. So we've already done CH. We know the CH electronegativity difference was 0.4. Now we have to do C and Cl. So if Cl is 3 and C is 2.5, that gives us a 0.5 electronegativity difference. It's slightly more polar than CH was. The main reason this is different is because all of our H electrons are getting pulled in toward my C, but my Cl makes my molecule lopsided. So electronegativity, electrons are then pulled toward my Cl. So this is overall going to end up being a polar molecule because the electrons are not being pulled evenly all the way around. They get pulled more toward my Cl. All right, now you can try the practice on your own. Ask questions if you've got them.